Hello everyone, trigonometry, and the unit circle. Okay, have a read through that, and let's start with the very first lesson, 4.1, angles and angle measures. So this is part 1. Let's revisit the idea of angles and standard position. So in geometry, an angle is formed by two rays with a common endpoint. So this would be a ray. So a ray is like, it starts with a point, ends in an arrow. Here's another ray, right? The initial arm, terminal arm, and that's how we form an angle. The starting position and the final position are called the initial arm and terminal arm of the angle respectively. If the angle of the rotation is counterclockwise, then the angle is positive. So counterclockwise is going this way. So counterclockwise. An angle is in standard position when its initial arm is on the x-axis and its vertex is at the origin of a coordinate grid. So initial arm is on the x-axis and its vertex is at the origin right there, origin 0, 0 of the coordinate grid. Okay, so this is an angle in standard position. Radian measure. So this is new for trigonometry, and we're going to work a lot with radians. So here's the rationale. Okay, in previous work with angular measure, 20-1, so grade 11, grade 10 math, and even some at grade 9, right? We've used degrees, right? Degrees as the unit of measure in order to simplify some of the calculations in calculus. So when you take calculus after this course, right, you'll work a lot with radians. It simplifies the calculations a lot. Okay, mathematicians developed an alternative angular measure called radian measure. Let's develop this idea of radian measure so you know where it comes from. 1 radian is the measure of the central angle subtended in a circle by an arc equal in length to the radius of the circle. So if this is the radius of the circle, okay, the arc subtended. So the measure of the central angle subtended in a circle by an arc in length, equal in length to the radius. So this arc, I know it's rounded, but if it's equal in length to the radius of a circle, that central angle is exactly 1 radian, shown in the diagram. So let me just make this bigger. This is 1 radian. Okay. Measure of an angle in radians equals the length of arc forming the angle divided by the length of the radius. That's the formula. Let's develop this idea of converting between radians and degrees. Consider a circle with a radius of r units. Complete the following. 1 complete rotation in degrees is 360. You need to put that little symbol there, degrees. The arc length for 1 complete rotation is 2 pi r. Okay, we know that, which is the circumference of the circle. The ratio of arc length to radius is, well, arc length of the complete rotation of a circle is 2 pi r over r, and that equals 2 pi. So 360 degrees equals 2 pi radians. 1/2 rotation in degrees is 180 degrees. The arc length for 1/2 rotation, okay, if a full rotation is 2 pi r, then 1/2 rotation, a half circle, is pi r. The ratio arc length divided by radius equals arc length of a half circle, pi r, the radius r. Okay, what's the angle measure in radians? Well, we're using this formula, remember, okay? Pi r divided by r is pi. So 180 degrees is an angle measure of pi radians. Let's keep going. Number 3, pi radians equals 180 degrees. If I divide both sides by pi, right, divide both sides by pi, I get my conversion factor. Okay, this is how we develop our relationship between radians and degrees. 1 radian equals 180 over pi degrees. 180 degrees equals pi radians. Let's go the other way. I divide both sides by 180. So my conversion factor to go from degrees to radians is pi over 180 degrees. Okay, to convert from radians to degrees, multiply by 180 degrees divided by pi. To convert from degrees to radians, multiply by pi over 180 degrees. Next page. Okay, very, very important note about symbols. I will be very strict about this. I consider the degree symbol like any other unit. If you tell me, like, remember the classic thing, and when we do measurement, like, remember grade 10 doing measurement, you calculate the volume of a sphere and you tell me, oh, Mr. Kim, it's 2080, and you don't put any units. Well, I'm wondering, 2080 what? Right? So units are important. So likewise with angle measure, units are important. So in math, the symbol, this thing, looks like a tiny little zero or a circle. Following a number means the unit of angular measure in degrees, okay, as in 360 degrees or 45 degrees. You must use that symbol. Very important. This is why. If there is no unit after a number, or there's the abbreviation rad, or the word radians, then the unit is in radians. For example, if you say 360, and you do not put a degree symbol, then I assume that's 360 radians. Okay? So please put a degree sign if you intend to say degrees. Okay? So I can write something like 2 pi radians. I can just say 2 pi, or I can say 2 pi rad, or I can write the radians in full. Okay? For example, if I type in sine of 90, so this is provided that you are in degree mode. Sine of 90 is 1. That's 90 degrees, but if I go to radian mode and I do sine of 90, I get something completely different, 0.89399666636, on and on and on, right? This value in degrees equals 1. This value in degrees equals 0.89399666636. They are not equal, folks. No degree symbol. Degree symbol. Be very careful. Okay, I'll pause here. Okay, take your calculator out and remind yourself on how do I go back and forth between radians and degrees in both of these main calculators, the TI-84 and the Casio FX9750G3. You will be doing lots of going back and forth between radians and degree mode in this unit and the next unit. Okay. All right, let's check our understanding here. Let's complete the table. One full rotation in degrees, 360 degrees. That's 2 pi radians. Half rotation, 180 degrees. That's pi radians. A quarter rotation, that's like a quadrant, 90 degrees, pi over 2 radians. 1/6 rotation, so 1/6 of 360, that's 60 degrees. Okay, that's pi over 3 radians, right? So it's like saying 2 pi, I want 1/6 of that. That's 2 pi over 3. Oops, 2 pi over 6, sorry, which is pi over 3. And that's how I get pi over 3. Okay? 1/8 rotation. Okay, 1/8 of 360 is 45 degrees. Well, what is it in radians? So 2 pi, I want 1/8 of it. That's 2 pi over 8, and that equals pi over 4 radians. Pi over 4 radians. 1/12 rotation. Okay, 1/12 times 360, that's 30 degrees, folks. Well, 2 pi, what is it in radians? 2 pi times 1/12, that's 2 pi over 12, and that's pi over 6 radians. Pi over 6 radians, okay? Example 1, let's practice drawing angles in standard position. Okay, remember standard position means initial arm starts on the positive x-axis, vertex at the origin, and we sweep an angle in the counterclockwise direction, ending at whatever angle we ask you to go to. Okay, so remember that. So Let's do some angles in standard position. So 150 degrees. Okay, quick reminder, remember that's quadrant 1, quadrant 2, quadrant 3, quadrant 4. You have to remember your quadrant numbers. I start at the origin. Here's my initial arm. I'm going to sweep. This is a positive angle, so I'm going to sweep in the counterclockwise direction. And 150 degrees is 30 degrees. If this is 180, folks, be accurate. 150 degrees is past this halfway mark, right about there. So there's my terminal arm. And theta equals 150 degrees. And let's convert each degree measured to radians and each radian measured to degrees. State the answers as both exact and approximate measures to the nearest hundredth. So 150 degrees, our conversion is pi over 180 degrees. Okay, and that is 150 pi over 180. Okay, if I reduce that, 50 goes into 100, sorry, 30 goes into 150 5 times. I have 5 pi on the numerator, and 30 goes into 180 6 times. So I have 5 pi over 6 radians, or approximately, if I'm asking to round, 2.62 radians. Okay. Letter B, negative 270. So it's a negative angle. I still start at the origin. Here's my initial arm. I'm going to sweep clockwise this time. Negative 270 degrees going clockwise. Here's 90, 180, and 270. Okay, and theta equals negative 270 degrees. Okay, negative 270 degrees. Let's convert that to radian measure. So here's my conversion factor, pi over 180 degrees. That equals 270, negative 270 over 180 pi. Okay. 90 goes into negative 270, negative 3 times. Oh, let me make this pi look better here. Pi, okay. Over 90 goes in 180 2 times, negative 3 pi over 2. And that is approximately, if I'm asking to round it, negative 4.71 radians. Okay, letter C, 7 pi over 6. So here's a quick tip, right? If you're trying to think about like, this is the problem you come into when you start to think about angles in radians. And I want you to start thinking about angles in radians. You practice enough, you'll start to be able to intuitively know when I say 7 pi over 6, you have an idea of where that's going to be. Instead of trying to do this whole thing like, oh, 2 pi radians is a full sweep of the circle, pi radians is half of it. Well, where is 7 pi over 6? Okay, I like to think about quadrantal angles. So I'll just do this in full. So if I start here, 0 radians, pi over 2, right? We know that's pi over 2. Okay, this is pi radians. This is 3 pi over 2 radians. And if we do a full sweep, it's 2 pi radians, right? So I like to think of, I'll write this note here, what is the nearest quadrantal angle? I've drawn them out here. So the angles associated with the end of each quadrant. What is the nearest quadrantal? Oh, let me write this again. Messy. Quadrantal angle. What is the nearest quadrantal angle? Make equivalent fractions and compare. This is how I would advise you to do it, to get your mind into the mode of measuring things in radians on a circle. Okay, because when you start to do this, we're not used to working in radians. When you start to do this, you start to think about radians in terms of what they are in degrees, then you figure out how far you sweep, and then you go back to the radians and rewrite it. I want to get you to the point where you can think about the radians, you see the radian measure, and you don't have to convert back and forth, okay, to degrees, then back to radians. Okay, so the way I think about it is, let's measure 7 pi over 6. I start on my, let's do it in blue for contrast. At the origin, here's my initial arm. It's a positive angle, so I'm going to go counterclockwise. Well, 7 pi over 6, I think of it as pi over 6 more than 6 pi over 6, which it's really just in disguise a pi radian angle. So that's just half of the circle. So this is how I like to think about 7 pi over 6. So I know I'm going to go, there's pi over 2 radians, there's pi radians, then I just go pi over 6 more. Pi over 6 happens to be 30 degrees, right? But I want you to think about pi over 6 as that amount, and I draw my terminal line here. And then this angle, folks, theta equals 7 pi over 6. Okay, I want you to start thinking about angles that way. Okay. All right, let's convert it to degree measures. So 7 pi over 6 times, what's my conversion factor? 180 degrees over pi. The pi's cancel. 7 times 180 divided by 6, well, that's 210 degrees. Let's do a quick check. Does this look like 210 degrees? We know it sweeps out at oops, just a second, folks. We know that it starts by sweeping out at 90 degrees. Oops, sorry. What is going on here? Let's try that again. Okay, let's get my highlighter. Sorry, folks. Okay, so we know it starts here, and it goes 90 degrees, 180 degrees, and then pi over 6 is 30 more degrees. So there's your 210 degrees. But we're practicing recognizing that that's 7 pi over 6 radians. So pi over 6 more than 180, or pi over 6 more than pi radians. Okay, next one, folks. Okay, negative 7.2. Remember, it doesn't say degrees. There's nothing written after it, so let's get used to it. It's radian measures. So think of this as negative 7.2 radians. How do I mark this? Before I go, right, when you say this, think in units of pi. Like, how do I know? Like, I start here. How do I know what 7.2 is? Like, where do you stop, right? That's why I think of pi units, right? So if I do negative 7.2 divided by pi, that's roughly negative 2.29 units of pi. We know what pi is, right? Pi is half of the circle, okay, in radian measure. So I divide by pi to give me a reference point of how far do I rotate. So I start my origin. Here's my initial arm. It's a negative angle, folks, so I go clockwise. So I start here. I need negative 2.29 units of pi. So I'm going to go 1 unit of pi. This is, oops, back that up. Let me start over. This is 1 unit of pi. This is 2 units of pi. And then 0.29 more. That's roughly a third of the way through another half rotation. So it's going to be about here. And then I'm going to draw my terminal arm right there. Okay. And then this is theta equals negative 7.2 radians. Let's convert radians to degrees. That's negative 412.53. Let's think of it as, right, that negative 2.29, that's like this part. Let me just bring this out here. That's like saying negative 2 pi, okay, negative 2 units of pi, which is a full rotation, plus negative 0.29 units of pi for the rest of the rotation. Think of it that way. So when I break down negative 412, think of it as I'm going negative, I'm going 360 degrees, I'm going one rotation, and then I'm adding 52.53 degrees more. So if I do, folks, I do 360 plus 52.53, I get 412.53. So let's take a look at our drawing here. Does that look realistic how we've swept this out? So let's take a look here. If I start here, right? Remember I started here. I'm going one unit, so I'm going 360. So let me start that over. Start here. This is 360, and then this visually looks about 50-ish degree, 52.53, but a little more than 45, right? So a little bit more than halfway through this quadrant, and that's my extra 52.53 when you add it up. That's our measure in, oops, I need degrees sign here, folks. Let's draw that degree sign, okay? So that's a handy way to think about it. This one's a little bit more, a little harder or not as intuitive to think about, but think about it in units of pi to help you out, okay? Next page. Coterminal angle. So this is a very important concept when we get to solving trigonometric equations later on. You'll have to remember the idea of coterminal angles because you'll have to state the general solution of trigonometric equations. So that's way later on. We got a lot more foundational stuff to go through, but we need to understand this idea of coterminal angle. It's exactly as its name suggests, right? Since we're rotating around a point and we're drawing a circle repeatedly, right? Angles in standard position, right, with the same terminal arms can be repeated over and over again, and these are called coterminal angles. So angles in standard position with the same terminal arms are coterminal. For an angle in standard position, an infinite number of angles coterminal with it can be determined by adding or subtracting any number of full rotations. So if you think about it, if I draw my axes here and I start here, there's my initial arm. If I draw one rotation and I stop here, well, that's 360. If I go again, another, that's 720, right? And you can go over and over again. You can see that there's an infinite number of angles possible. So that's why there's this idea of coterminal angle. Instead of like saying, oh, 360, 720, and then on, we have this generalized format of how to state a coterminal angle. Angles coterminal with any angle theta can be described using the expression. So here's the two ways. Theta plus or minus 360 degrees times n. Or theta plus or minus 2 pi n, where n is an element of, what is this n? This is natural numbers. Okay, folks, remember number systems. What's natural numbers? That's 1, 2, 3, ... on and on. Okay, you're counting numbers. Or the other way, this is Mr. Kim, I prefer this. Theta plus 360 degrees and then n, or theta plus 2 pi n, where n is an element of, what is I? Ooh, this is integers, folks, right? Integers, where n does not equal 0, okay? So n does not equal 0. Okay, remember n is your natural numbers. And that is 1, 2, 3, on and on, also known as your counting numbers. And then integers, I, that's integers. And that is numbers like ... -3, -2, -1, 0, 1, 2, 3, dot, 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 okay? But for the purposes of stating the general solution for like what are all the coterminal angles, right? N does not equal 0. So in this case, we will not use 0 when we're stating general solutions to what the coterminal angles are for a particular problem. Okay? All right. Let's finish this part. The principal angle. Okay, so since there are an infinite number of coterminal angles, we need a generalized way to think about what a coterminal angle represents. So we have this idea called a principal angle. The principal angle of a set of coterminal angles is the smallest positive rotation of the angle with the same terminal arm. The principal angle is between 0 and 360 degrees, or between 0 radians and 2 pi radians. Okay? Let's do an example. For each angle, determine one positive and one negative angle measure that is coterminal with each angle. Identify the quadrant the terminal arm lies in. State the principal angle. Okay? 40 degrees. Let's think of it this way. Theta plus 360 degrees n, where n is an element of all integers, but n is not equal to 0, right? N does not equal 0. Okay? If I use this formula here for the general form of the coterminal angle, 40 degrees plus 360, let's say n equals 1. So we're going to state one positive, one negative angle measure that's coterminal to 40 degrees. That is 40 plus 360. That's 400 degrees. So that's a coterminal angle. Let's do a negative angle, 40 plus 360. This is why I like to use the integer format, not the natural number. I put a -1. So I do this because I like integers, because I don't want to worry about this plus minus thing. So I just think about integer values, right? So -3, -2, -1, 1, 2, 3, on and on, okay? So 40 degrees plus -360, that's -320 degrees. Okay, let's look at this visually. So if I go 400 degrees, I'm going once around. That's 360, and I go 40 more, a little less than halfway through quadrant 4. Okay. Oh, oops. Oh, hang on. Back up. Sorry about that. I screwed that up. Let me try this again. Here's my initial arm. Okay. Positive 400. I'm going this way. This way, this way. Sorry, folks. So I'm going this way. That's one full rotation. And then 40 more degrees is a little bit before the halfway point in quadrant 1. So there it is. That's theta equals 400 degrees. Okay, or the other way to think about it is, here's my vertex, initial arm, -320, right? So I'm going, if I think of it this way, I'm going 40 degrees shy of a full rotation. So I'm going to go 90, 180, 270, and then stop 40 degrees shy of a full rotation. It's the same angle because they're coterminal. So theta equals -320 degrees. Let's answer the rest of the question, folks. This is identify the quadrant arm, quadrant the terminal arm lies in. So terminal arm in quadrant 1. State the principal angle. Well, the principal angle is the smallest positive angle that is coterminal. So the principal angle is the smallest positive rotation angle with the same terminal arm. So principal angle is 40 degrees. Okay, second one. -430 degrees. Theta plus 360 degrees times n. where n is an element of integers, n does not equal 0. Okay, so negative 430 plus 360. Let's pick an n value of 1 rotation, and that equals negative 70 degrees. That's one coterminal angle. Negative 430 plus 360 times negative 1 equals, oops, no, let's not do that because this is my negative angle, I need a positive angle. So I'm going to do this. Let's just pick the integer 2. That's going to be negative 430 plus 720. That equals 290 degrees. Okay, let's draw a little picture. Okay, here's my terminal arm for negative 70 degrees. That's going to be most of the way through the quadrant, fourth quadrant. Okay, so I'm going clockwise because it's negative. And I'm going to stop right about there, 20 degrees shy of the 270 degree mark, right? So right there. So that's theta equals negative 70 degrees. Okay, if I think about, so that's going to be in quadrant 4. Okay, let's think about the positive rotation angle, so coterminal angle. We're going 290 degrees, so I'm going to start with my initial arm. Positive angle, so I'm going to go counterclockwise, so there's 90, 180, 270, and then 20 degrees more is right about there. And you can see it ends up in the same quadrant. So this is theta equals 290 degrees, and this is also a terminal arm that ends in quadrant 4. What's my principal angle? So this is the smallest positive angle that is coterminal, and so that is a principal angle of 290 degrees. Next one, folks, let's keep going. 8 pi over 3. Ooh, let's do our first one in radian measure. So 8 pi over 3, I'm going to go theta plus 2 pi n. That's the general form for stating coterminal angles, where n is an element of integers and n does not equal 0. Okay, so that's 8 pi over 3 plus 2 pi. Let's use an n value of negative 1. Okay, that's going to get us our positive angle. So that equals 8 pi over 3 plus 6 pi over 3 times negative 1. That's 8 pi over 3 minus 6 pi over 3, and that equals 2 pi over 3. Okay. Okay, that's that one. Let's do our negative angle. So 8 pi over 3, let's use this general format, plus 2 pi. How will I get a negative angle? Let's multiply by negative 2. So an n value of negative 2. That equals 8 pi over 3 minus 4 pi. So 8 pi over 3 minus, that is 12 pi over 3. And so that is equal to negative 4 pi over 3. Okay. Let's sketch these out. So I have my first coterminal angle, 2 pi over 3 and negative 4 pi over 3. Let's do this one first here. Okay, I'm going to start. This is a positive angle, so I'm thinking of 2 pi over 3. I'm thinking of quadrantal angles. I'm thinking of 3 pi over 3, which is the same as pi radians, which is a half circle. So 2 pi over 3 is pi over 3 radians short of a half rotation. So I start here, and pi over 3 is 60 degrees, so it's going to be right about there. Okay. Let me make this a little bit more accurate. Okay. So pi over 3 is 60 degrees. 2 pi over 3 is 120, so we should end up right about 30 degrees into the quadrant 2, right? So this is theta equals 2 pi over 3. That's our first angle. Let's do our next one here. I start here. It's a negative angle. Okay, so negative 4 pi over 3. I'm thinking of quadrantal angles. Well, I'm going clockwise, so I'm going to go I'm going 1/2 rotation plus pi over 3 plus pi over 3 more in the clockwise direction. So because negative 4 pi over 3 is pi over 3 units more than a half rotation. So I start here. Here's my half rotation, then pi over 3 more, which is 60 degrees. So a little bit into there. And then we draw our terminal arm. This is theta equals negative 4 pi over 3. Okay, and then this is quadrant 2, and this is quadrant 2 as well. Okay, let's state our principal angle, folks. So last thing, this is our principal angle. It's the smallest positive angle that's coterminal to all the other angles. Okay, and that's our principal angle, smallest positive angle between 0 and 2 pi radians. Okay, one more, folks. Negative 15 pi over 2. Ooh, okay. Let's do this one. Theta plus 2 pi n, where n is an element of integers and n does not equal 0. Okay. Negative 15 pi over 2 plus 2 pi times 1. That's negative 15 pi over 2 plus 4 pi over 2. And that equals negative 11 pi over 2. Okay, let's put a box around that. Let's do a positive angle. So let's pick an appropriate n value that gives me a positive coterminal angle. So 2 pi. Let's pick 4. That should get us squarely in the positive area. So that's negative 15 pi over 2 plus 8 pi over, plus 8 pi. Okay, that's negative 15 pi over 2 plus 16 pi over 2, and that is pi over 2. Okay, let's put a box around that. Let's draw this first angle. Let's see what quadrant it ends up in. Let's start here. So this one. Yep, this one. What is that? Come on. So this one. I'm going to start with my initial arm. It's a negative. Let's think about this, okay? Try to think in terms of radians, units of pi radians, okay? So negative 11 pi over 2. I'm thinking of negative 12 pi over 2, which is negative 2 pi, which is one full rotation. So negative 11 pi over 2 is pi over 2 radians short of a full rotation. So I start at the initial arm. I'm going clockwise because it's a negative angle. So here's 1 pi. I'm going to stop pi over 2 radians. Oops, sorry. Let me do that again. I'm going to stop pi over 2 radians short of, yeah, so it's like 90 degrees short of a full rotation. So I'm going to go this way. Oh, sorry. Let me back that up. Start all over here. So I'm going to draw my graph here. This is how it's going to look. Let me do this correctly. So I'm going to start with my initial arm. Okay. Negative 12 pi over 2. That's negative 6 pi. So I misspoke. This should be 3 full rotations. So we need to go 3 full rotations, but I'm going negative 11 pi over 2. So I'm stopping pi over 2 units short of 3 pi rotations. Sorry, 3 full rotations. That hopefully makes more sense. So let's go. 1 rotation, 2 rotations, and then I'm going to stop pi over 2 radians short of 3 full rotations right there. And then this is my terminal arm. So this big spiral thing, that is a theta value of negative 11 pi over 2. Okay, and I end up in between quadrant 1 and quadrant 2. So right on the line, on the border. Okay. Okay, I screwed that up. Sorry about that. Hopefully that makes sense. So I'm going to do another one here. Let's do pi over 2 radians. I'm going to start at the origin. Here's my initial arm. I'm going to sweep pi over 2 radians. It's a positive angle, so I'm going the clockwise or counterclockwise direction. So here we go, pi over 2 radians. Well, that's just one quadrant right there. So I'm stopping here. Is my terminal arm. This is theta equals pi over 2 radians. Okay. Sorry about that. I screwed up that first one over here. Hopefully that makes sense. I corrected it. Okay. So this is between quadrant 1 and quadrant 2. Okay. Right on the border. And the principal angle, well, this is your principal angle. It's the smallest positive rotation angle with the same terminal arm. So this is pi over 2 as my principal angle.